So now that we've talked a bit about how Java splitterators work in the context of parallel streams, let's start talking about how the apply phase gets used in Java parallel streams, talking about the common fork join pool and giving you an idea of how it actually works. So what the common fork join pool does is it is used to process the chunks created by the parallel splitterator using parallel processing in a very clever and interesting way. And so that's what we're going to talk about here. So the chunks that are created by a splitterator, by a parallel splitterator, are processed in the common fork join pool. You can read more about the fork join pool here in this paper written by my good friend and colleague Doug Lee. As we've talked about briefly before, and now we'll go into more detail, a fork join pool in general provides a high-performance, fine-grained task execution framework that supports Java data parallelism. So the data elements are the things that are run in parallel, sometimes referred to as the SIMD model, single instruction, multiple data model. This particular abstraction is used, as we've seen, for many other frameworks, including parallel streams and completable futures. And so we're going to focus here on the use of the fork join pool, and more specifically, the common fork join pool in the context of the parallel streams environment. But I want to talk briefly about what fork join pool does first. So fork join pool implements the executor service interface. We're not going to talk much about executor service in this class. That's really a concurrent object-oriented programming topic. But essentially, it defines some methods for submitting tasks to be run in the background in thread pools. A fork join pool executes something called fork join tasks. And we'll talk about what a fork join task is in a second. You can think of a fork join task as basically a means of computation that's very lightweight. And the fork join task in particular associates a chunk of data, which is typically a piece or a partition of the overall data source, chunked up into pieces by a splitterator, of course, along with some computation on that data. And so it's that connection between a chunk of data and a computation that's the interesting part of what the common fork join pool, and more specifically the fork join task, will run. A fork join task looks a bit like a thread, but it's a lot lighter weight. So a thread has a runtime stack, a thread has its own registers, a thread has its own local storage. A thread is executed typically by a kernel abstraction in the operating system kernel, typically a kernel thread. So a Java thread runs in the context of a kernel thread. And a fork join task has none of that. A fork join task doesn't have its own runtime stack. It doesn't really have its own registers. It doesn't have its own thread local storage. It has a much leaner and meaner way of being able to do things. And as a consequence of that, because it's leaner and meaner, you can have a very large number of fork join tasks that are running atop a much smaller number of Java threads, or what are called worker threads. By the way, we had talked briefly about this earlier in the course, about the new model of Java threading that's coming out at some point with Project Loom. And in that context, the fork join tasks are basically what we would think of as virtual threads. And the worker threads down here, the Java threads, are what we would now call platform threads with the newer Java programming model. You can think of parallel streams as essentially a nice, user-friendly, functional wrapper facade for the underlying fork join engine. So fork join engine is object-oriented programming. Parallel streams and streams provides you with functional parallel programming. And so you can think of it as just a way to encapsulate all the cool performance enhancements that are provided by the common fork join pool, but have a nicer patina, a nicer way to look at it and program it. Now, you can, in fact, program directly to the fork join pool API, and I will show you some examples of that here shortly. However, it is more painful. Those of you who have seen Lord of the Rings will remember the famous wizard battle between Saruman and Gandalf, where Saruman says, you know, I gave you a chance to come willingly, to join me willingly, but you've elected the way of pain. So if you choose to program with the fork join pool, you are electing the way of pain, and I'll show you that in more detail. By the way, is anybody here watching the new Rings of Power special? So who do you think the spaceman is, the guy who came from outer space? We think he's Gandalf, but we're not really sure. So Tolkien probably doesn't really say the origin of how Gandalf came to Middle-earth, but maybe it was in a comet. We'll find out. So there's a bunch of different examples showing how to use the common fork join pool. There's a nice one here that shows how to search for all the words in the phrases in Shakespeare using the fork join pool as opposed to parallel streams. And we'll take a look at a different example in a minute. All the parallel streams within a process, within an application, all share the common fork join pool. So there's only one common fork join pool, and all the parallel streams will share it. Why do they do that, you may ask? It's in order to be able to optimize the utilization of processing resources by having a way to know globally within a process what cores are being used at any given point in time. So again, you can think of it like, Cerebro or something like that, and it's got a global view of everything that's happening at that point within the process. And that helps overall utilization because, as we'll see in a moment, when one worker thread in the common fork join pool runs out of stuff to do, it goes and steals work, hence the little stealing thief icon here. It steals work from something else. This concept of global versus local resource management, or another way to put it is giving preference to global management of resources as opposed to local management, is something else you see a lot in other contexts. For example, Java's heap that they use to allocate memory using operator new in Java. That comes out of the global heap. So all the memory is allocated out of the same chunk of memory. And the idea there is that that can give the heap manager, the garbage collector, and so on, a more effective way of keeping track of all the different resources that are memory related in that program. You'll see other things. You'll find if you ever take courses on administration of companies or universities, there's all these tug of war between do you have it centrally managed, do you have it managed by each school or each unit or whatever. And there's really no one right answer, but these are what they've chosen here for a variety of different reasons in Java. Something else that's quite interesting with the fork join pool, be it the common fork join pool or a more specific one that you might make that's not the common one, is there are very, very few knobs available to control the features and behaviors of the pool. And this simplicity is intentional. So if you take a look at the fork join pool, you'll see that there's a relatively small number of methods, and there's not much you can do to control what happens. And you can watch this video by Doug Lee where he explains the reason behind this. In contrast, the thread pool executor, which is another thread pool implementation that's part of classic OO Java, it has all kinds of hooks and knobs and ways to control it. So you can have control over the number of threads in the pool, both the core size and the max size. You can determine how long each thread lives. You can define the work queue. You can define how you make the threads. There's all kinds of things that you have as options. So it's kind of like the difference between a spork, which is a spoon-fork combination, and a Swiss Army knife, which has lots and lots and lots of features, right? So thread pool executor, lots and lots of features. Fork join pool, very, very simple. There are a handful of things you can do to manage the fork join pool, or the common fork join pool. One is you can set the desired number of threads you want it to have when the program starts up, and we'll talk about a bit about that. Or you can also use something called the manage blocker, and we will talk about that as well. And I'll show you some examples of the benefits of doing the manage blocker here in just a moment. Okay, so that's the end of part one of this discussion.